Greetings, ladies and gentlemen. I am Noel Moire. I attend Benedict College, and today I'd like to share with you my research project on heavy metal adsorption using shrimp shells derivative. This is my outline for today's presentation, from introduction all through to conclusion and future works. Heavy metals such as lead, copper, arsenic, and chromium pose a threat to the environment, and they are introduced to the system through anthropogenic activities such as agriculture and industrialization. And these heavy metals are toxic to plants and animals, and to human beings they may be carcinogenic, mutagenic, and may result to death. That is why in this research we are investigating the application of shrimp shells as possible alternative to conventionally used activated carbon. Activated carbon is expensive and its mode of acquisition is environmentally unfriendly. However, on the other hand, shrimp shells are derived from low-cost and readily available materials and therefore can be used as alternative to activated carbon. My objective in this study is to study the effects of multiple metal ions in the binary adsorption system versus singular system. A binary system is a typical imitation of the industrial effluent, which constitutes of several heavy metal ions. A binary system involves two metal ions in the same aqueous solution versus a singular system which has just one metal contaminant. I would also like to investigate the adsorption properties of shrimp powder and shrimp chitin and analytical reagent chitin. I would also like to evaluate the effects of adsorbent dosage on adsorption. For material fabrication, shrimp shells were reduced to shrimp powder through ball milling. To obtain shrimp chitin, a two chemical process stage was performed: demineralization using hydrochloric acid and deproteinization using sodium hydroxide. These are some of the instrumentations that were used for the characterization of the materials: the X-ray diffractometer, the Buhner-Emmet stellar, and the Fourier transform infrared. This is the XRD analysis, which was used to affirm that we actually obtained chitin in comparison to analytical chitin. And analytical reagent chitin was purchased to be used as our control in this experiment. We can vividly observe at the 9° 2 theta and the 19° 2 theta there are two strong peaks which indicate the presence of chitin, which are not present on the shrimp powder. And the BET analysis was used to study the surface area and the pore size of the adsorbents. We can observe that our materials are mesoporous, as they have pore size ranging from 175 to 300 angstrom. The XRD was used to define whether our materials are crystalline or amorphous in nature, and the percentage shows that our materials were very amorphous. This is the Fourier transform infrared spectra, and the Fourier transform infrared is used to identify the functional groups present in the adsorbents. And in these adsorbents, we observe that they contain an hydroxyl group, a carboxyl group, a carbonyl group, and also an amide group. Functional groups play a very important role in ligand complexation during adsorption. We performed a batch study in singular system and the binary system. My main focus today is on this binary system, whereby 50 milliliters of metal contaminant in a ratio of 1:1 was utilized to make up 100 milliliters, and adsorbent dosages ranging from 0.5 grams to 2.0 grams were also utilized. A contact time of 30 minutes was used with agitation for the adsorption process, and the final concentration of the metal contaminants was obtained using the atomic absorption spectrophotometer. Different metal contaminants had different initial concentrations, as shown on this slide. And this is a mass bias analysis of the batch study. Assuming a steady state, whereby our input is equal to our output, the volume times the initial concentration minus final concentration will be equal to adsorbent dosage multiplied by initial adsorbent capacity minus the final adsorption capacity. At time t, the final concentration will be equal to concentration at time t, whereas our final adsorption capacity will be equal to adsorption capacity at time t. And at time 0, there is no adsorption, meaning the adsorption capacity will be 0. And trying to solve for Qt, which is the adsorption capacity at time t, we utilize this equation, V times the initial concentration minus final concentration divided by the adsorption dosage. Adsorption capacity is the amount of heavy metal removed by 1 gram of adsorbent dosage, and it's in milligrams per gram. The following slides will show the results obtained, which are in adsorption capacity against time, adsorption capacity on the y-axis, and time in minutes on the x-axis. For the top part, we have the single system graphs, whereas the bottom graph represents the binary system. This is our legend with the complete lines for this particular graph showing lead, and the incomplete lines represent copper at different dosages. We can observe that for the lead removal using shrimp powder, we have a dosage dependent trend, and the 0.5 gram has the highest adsorption capacity, whereas in the copper removal, we also note that 0.5 gram had the highest adsorption capacity, but the trend shows an increase in adsorption capacity with an increase in time, whereby 30 minutes you obtained a very high adsorption capacity removal for copper. However, in the binary system, we observe that the lead removal was higher compared to the copper removal. However, we can note that we have an increase in the adsorption capacity of lead, and we also have an increase in the adsorption capacity of copper, as noted in the graphs of the binary system. Using shrimp chitin as our adsorbent, we note that 0.5 grams still had the highest adsorption capacity, whereas in the binary system, we have an increase in the adsorption capacity of both lead and copper. The same trend is observed whereby when we used analytical reagent chitin, which is our control, we note that we have an increase in the removal of both lead and copper in the binary system as compared to the single system. And the subsequent slides, I'll be showing you my second binary system, which was for chromium to cadmium. And we have the top part shows the single system, and the bottom part still shows the binary system. And the legend incomplete lines are for cadmium, and the complete lines represent chromium. In the removal of chromium in the single system, we note a 0.7 milligram per gram removal of chromium and a 0.5 milligrams per gram removal of cadmium. However, this adsorption capacity changes, whereby in the binary system, the removal for chromium increases to up to 0.9 milligrams per gram, whereas that of cadmium reduces to close to 0.4 milligrams per gram. Using shrimp chitin as our adsorbent, we observe an increase in the removal for chromium and a subsequent decrease in the removal for cadmium in our binary system test. And using analytical reagent, which is our control, we note the same trend, whereby the removal for chromium increased, whereas that for cadmium increased, but just for 0.5 gram. The other adsorbent dosages showcased a decrease in the removal for cadmium. And with these results, it can be highly visible that 0.5 gram attained the highest adsorption capacity compared to other adsorbent dosages, and shrimp powder had the highest uptake rate for lead of 8.5 milligrams per gram versus 8.2 milligrams per gram using shrimp chitin and 6.8 milligrams per gram using analytical reagent chitin. We had a significant increase in the adsorption of copper from the single system in the binary system. And if the effects of ionic interaction in binary system can be termed as synergistic or antagonistic, whereby synergism means that one metal ion will increase the uptake rate of another metal ion, and this was experienced in the lead to copper binary system. And this is due to the formation of ligand complexes on the adsorption surface using one of the metal ions, and therefore increases the removal of the other metal ion. On the other hand, antagonism represents inhibition, whereby we have competition for active adsorption sites, and this was experienced in our chromium to cadmium binary system. This is due to the formation of non-adsorbable complexes, and that will lead to an antagonistic reaction. This work does not stop here. In the future, I would like to assess the regeneration properties of the adsorbents. I would also like to evaluate the application of crab powder as a low-cost adsorbent. I would further have isothermal and kinetic studies performed, and perform also statistical analysis. And to make this work possible, I would like to thank the Department of Energy grant, my institution Benedict College, Mr. Tiana Rosa, who is one of the most helpful people I've encountered in this life, and my research colleagues. Thank you very much for listening to my presentation, and in case of any questions, you can contact me at my email address or my phone number as shown below. Thank you very much again.